don't know that for sure. It just seems like it goes off the fast.
Huh. So, as we stated earlier, we're most often concerned with the average power in loads, not the instantaneous power that we just looked at. Since voltage and current are in phase in purely resistive load, power average is equal to I RMS times V RMS. However, if we were to just apply this formula to loads containing reactive circuits, you know, inductors and capacitors, we wouldn't get the correct calculation. If an AC circuit contains any sort of resistance, there is always a power component associated with the magnetic field of inductance and the electric field of the capacitance. The power associated with these two fields, the electric and magnetic fields, it's not converted into heat as it is with the resistance, but what happens is it's stored during part of the AC cycle and then discharged during another part of the cycle. So we say it's stored and charged during the AC current and voltage cycles. Therefore, circuits containing a complex impedance will have complex power, and it consists of what we call two parts. The first is the power that's consumed by the load. We call this a real power. Some people call it active power. This is the power that's created and converted into heat. And then the second is the power that's stored in the magnetic field of an inductor and in the electric field of a capacitor and is absorbed and released by the electric and magnetic fields. We call this reactive power. So we're going to now look at real and reactive power in AC loads. So we can understand the different components of the AC power waveform if we look at our standard power equation, right? So I've just rewritten the power equation from from our previous slide where we multiplied the sinusoidal voltage by the sinusoidal current, right? So we resulted with Vmax Imax over 2 times the cosine of the phase shift between the voltage and the current waveform, plus Vmax Imax over 2 times the cosine of the phase shift times the cosine of 2 times the angular frequency of the voltage and current, assuming that they're the same. Vmax Imax over 2, and then we have these sine quantities. A lot of times we're going to simplify this equation, not write it out in all that complex detail. We're just going to write it as capital P plus capital P cosine of 2 omega t plus capital Q sine of 2 omega t. So capital P plus P cosine 2 omega t plus Q sine 2 omega t. What we're saying here is that P is equal to Vmax times Imax over 2 cosine of theta, right? We just performed a substitution there. And that Q is equal to Vmax Imax over 2 sine of theta, right? This thing here, P, is called real power. It's the real power. Q is called the reactive power. Let's look at each of these terms by examining power in circuits that are purely resistive, purely inductive, and purely capacitive in turn. If we've got a purely resistive circuit, if the circuit to which power is being delivered is purely resistive, that means the voltage and the current have to be in phase. That means theta V equals theta I, and this term here goes to 0, right? I can plug in a 0 for theta since they're equal. There is no phase shift. So what's cosine of 0? It's 1. What's cosine of 0? It's 1. What's sine of 0? 0. So this whole thing for a resistive circuit, only P of t is just going to be Vmax Imax over 2 plus Vmax Imax over 2 cosine of 2 omega t. Right? we've got here we've got we can, for this purely resistive circuit, we could say that that is then equal to P plus P cosine of 2 omega t. Right? So what we're showing here is instantaneous real power in a resistive load is always positive and has twice the frequency of the voltage and the current waveforms. All right, we've got Vmax Imax over 2. We've then add to it Vmax Imax over 2 times the cosine of 2 omega t, right? That means that the power waveform in a purely resistive circuit is shifted up the graph by Vmax Imax over 2. Its total amplitude is Vmax Imax over 2. That means, you know, cosine oscillates between -1 and 1. So the maximum or the minimum value this could have is 0. The maximum value it can have is going to be, you know, Vmax Imax over 2 plus Vmax Imax over 2, or, you know, just Vmax times Imax, right? So if we think about it that way, purely resistive circuit, because of this cosine term and these offsets, power is always positive. What this does is it proves that power can't be extracted from a purely resistive network. All of the electric energy is dissipated in the form of heat. It's positive power. The measurement of power associated with purely resistive circuits, real power, indicates that the power associated here is in joule heating. And the units we use to measure this quantity are the watt, right? Should be totally familiar. What if the circuit to which power is being delivered here is purely capacitive? Well, in this instance, the voltage is going to lag the current by 90 degrees. That means theta in this formula is going to be -90. So let's plug in -90. We put in a -90 here, we put in a -90 here, we put in a -90. What happens? Cosine of -90, 0. Cosine of -90, 0. Sine of -90, -1. So this whole thing is going to reduce to P of t for a purely capacitive circuit is just equal to minus Vmax Imax over 2 sine of 2 omega t. So this is kind of instancing, or is interesting. We look at if we were to average over one period the power of this, we see that there is no offset in this case. Purely capacitive circuit, there's no offset. That means the average value of this thing, the average value of over one waveform is 0. Half the time the power is positive, half the time the power is negative. Over one full cycle, they cancel each other out. In a purely capacitive circuit, the power is continually exchanged between the source driving the circuit and the electric field associated with the capacitive element. Sometimes it's charging up that electric field and putting energy into it. Sometimes during the negative half cycle, energy is being extracted from the capacitive field. We'll note that the Q term here is positive for inductors and negative for capacitors. That's just kind of we've got a negative term here. It's often colloquially stated that inductors absorb what we call reactive power, and capacitors deliver capacitive power. Deliver meaning it, you know, there's a minus sign in how much reactive power is actually being consumed here. So what if the circuit is purely inductive? Well, in this case, the voltage leads the current by 90 degrees, meaning that theta is 90, right? So in this time, this goes to 0, this whole term goes to 0, sine of 90 is 1, we're left with Vmax, Imax over 2. sine of 2 omega t, right? Because that goes to 1. So very similar situation to the capacitance, but in a purely inductive circuit, again, the average power is going to be 0. No transformation of energy is taking form, or no transformation of energy into heat is taking form, excuse me. Instead, what's happening is the instantaneous power is being absorbed by the magnetic field and then being released by the magnetic field at a frequency of 2 omega. When we can see during the positive half cycle of P of t, energy is being stored in the magnetic field associated with the inductive elements. During the negative half cycle of P of t, energy is being extracted from the same field. The measurement of power associated with a purely inductive circuit, we call that that Q value here. Indicates that the power is associated with the reactive circuit element. So you see the Q came into play with the inductor here, and then on the previous example with the capacitor. To distinguish the reactive power from the real power, we use a different unit here. It's called volt amps reactive. And it's given the symbol VAR. Most commonly, VARS is how that's pronounced. And you'll notice that, well, the product of voltage and current is a watt, right? Well, it's also a volt times an amp. Here we just call it volt amps reactive. Again, I say this a lot about electrical engineers. We're not the most creative bunch on the planet, but volt amps reactive. It's reactive power, right? Okay, so let's do a kind of a nuts and bolts example of calculating real and reactive power. We want to calculate the real and reactive power in a circuit if we know the voltage in the current waveform. So in this circuit, we know that the voltage is given by 100 cosine of omega t, and the current flowing into the network is measured to be 4 sine of omega t minus 30 degrees. So it is out of phase with the voltage waveform, and we could say therefore it's, we've got a complex impedance. We also then, when we do our analysis, want to interpret the results to state whether the network is absorbing or delivering real and reactive power. So what is this saying, I guess, is the first thing that we want to look at. So what we've got is we've got some arbitrary network Z, and what do we know about Z? Well, we've stuck an ammeter in here, and we're measuring its current in, and then we've stuck a voltmeter across it, and we've measured its voltage, right? And what we determined was that the voltage function, V of t, through our measurements, we determined that it was 100 cosine of omega t. And through our measurements, we determined that the current function was 4 times the sine of omega t minus 30. So let's calculate real and reactive power for that. Well, the first thing that we need to notice is that I tried to trick you here, right? We have current represented in terms of the sine function, and we know that when we did our power calculations, we multiplied in voltage and current in terms of a cosine. So it's just easier for us to go ahead and convert this current over into a cosine term. So step 1 really is going to be I of t is going to be 4 times the sine of omega t minus 30 minus 90. So that's equal to 4 times the sine of omega t minus 120 degrees. All right. Remember that in our calculations, theta is equal to the voltage phase shift minus the current phase shift. Here we've got the current phase shift of minus 120, right? And so that's 0 minus negative 120. That's just a phase shift of 120 120 degrees, right? So we've got a total phase shift between the voltage and current of 120 degrees there. So let's go ahead and use our formulas for calculating the real and the reactive power. We have Q is going to be, from our formulas, we've got Vmax times Imax, and remember we divide that by 2, so P is equal to Vmax Imax over 2 cosine of the phase shift. And so from our previous slide, that's 100 volts times 4 amps divided by 2. And cosine of theta was cosine of 120. Cosine of 120. And that gives us minus 100 watts. And then Q is going to be 100, or sorry, it's Vmax Imax over 2 again. And that's just going to be sine theta. So we get 100 times 4 amps, we divide that by 2, multiply it by the sine of 120, and we get 137.21 vars. 173.21 vars. So what's this telling us? Well, the negative value obtained for the real power is going to indicate that for this circuit, the network is actually delivering, not absorbing, real power, which is interesting. The network is delivering real power, not the source. Power is flowing out of the network based on these measurements of current. It's not flowing into the network as we would have expected. The positive value obtained for the reactive power means that the network is absorbing vars. It means real power is flowing into the circuit. And remember, we said that inductors consume vars, capacitors supply vars. Inductors have positive vars associated with them. So we're seeing that this network overall appears inductive as a circuit element.